Hello. Today we're going to go ahead and take a look at the Hooke's Law Lab. This is a virtual lab we're doing using the Colorado PhET site. And we'll go ahead and download the simulation. I'm going to jump right to past this introductory part, messing around with it, looking at generally what's happening with mass on a spring, and jump right to this second part of here where we're actually doing the lab and taking the data and deriving Hooke's law, that equation for the force of a spring. So I want to kind of jump right to that part. So we're going to go to the lab section here. And it gives us this spring. I'm going to leave that spring constant alone. We're going to be trying to derive that as part of what we're doing here. And so I have this set spring, and that spring constant tells you how stiff or how strong the spring is. And so what we're going to do is go ahead and put some known masses, hang them on the end of the spring, and see how far that spring stretches. And that's really what we're trying to find here. We want to find the relationship between how hard the spring is pulling and how far it gets stretched. And the reason that's going to work is we're going to go ahead and do a little force diagram for that mass that's hanging on the spring. You say, okay, well, what would that look like? Well, if this is that mass that's hanging on the spring, you'd say, what forces are acting on that mass? Well, there'd be a gravitational force pulling down on it, and then there'd be that spring pulling up. And if we look at this specifically at the point where that mass has come to equilibrium and it's just resting there, then these two forces will be the same. And since we know the mass of the spring that we're hanging, we know how big the gravitational force is, then we know how hard the spring's pulling, because those forces have to balance out. And so even though we're not directly measuring the force of the spring, we know it's got to be equal to the weight of the mass that's hanging on the end of the spring. So that's kind of the plan. So the plan is that we'll make a graph, and on the vertical axis, we'll put then that force of the spring, which we'll calculate as just being equal to mg. And on the horizontal axis, we can look at how far it stretches, okay? How far that spring stretches. Okay, and hopefully we'll be able to get a nice relationship and derive an equation for the force of a spring. So heading back here. So what we're going to do, we're going to go ahead and set this up. It asks you to go ahead and if I click this, it'll go ahead and it'll drop in this line for me showing the unstretched position of the end of the spring. Okay, they're going to call this like the natural length of the spring. This line shows how long this whole spring is. And we're going to go ahead and take a ruler here so we can measure just the stretch. And that's important. We're looking at is not the total length of the spring. We're looking at how far it's stretched by. That is a key part of Hooke's law. And then we can go ahead and a useful thing to do here is to turn up the damping. Now, what damping is it's looking at the effects of internal friction on the spring. If I go ahead and I turn the damping off, and I were to hang a mass from the spring and let go, it's going to wiggle and jiggle back and forth like that. If I turn the damping on, it's like turning on the internal friction as those atoms in the spring are having to slide past each other, generating heat, and that's going to slow down the spring to a rest so we can measure the length that it's stretched to. So I'm going to turn my damping up all the way. I want that. Now, so what our plan here is then to go ahead and change the mass that we're hanging, therefore changing the gravitational force, which will then change how hard the spring is pulling. We'll be able to see how far it stretches. That's the plan. So let's pick some values. The general rule of thumb that we use in this class is that we like to have a factor of 5 between the smallest and largest value that we choose. So maybe we'll start with the smallest we can do here, 50. And we'll go ahead and we'll put that 50 gram mass on there and see where it ends up, right? And then we want to read off how far it's stretched. And you say, well, gosh, that's kind of tricky. There's this click we can do here for movable line, which might make it a little bit easier to line this up with the end of that arrow showing how far it's stretched. And now we could read this off. I don't know about you, but this, to me, it says this is in centimeters. And so to me, that red line looks like it's right in the middle between 8 and 9 centimeters. I'm going to go ahead and call it 8.5 centimeters. I could just jot my data down if we'd like. Perhaps jotting that down here. Or do you want to type it directly into the spreadsheet? Let's just go ahead and skip a step and go directly to the spreadsheet. Let's see here. We'll say this is going to be Spring Lab. And say we're going to go ahead and set up now. We'd like to do our columns X and then Y next to it. We had decided that we were going to try to make a graph that had the stretch on the X and the force of the spring on the Y. And so what I'm going to need to do is let's go ahead and make this life easier if I have X and Y columns next to each other. So this is going to be the stretch. Okay, and that's going to be, I'm going to convert it on the fly to meters from centimeters. I could do a calculated column or whatnot, but let's just go ahead and do that in our head. It's easy enough to move decimal point 2 places. And then this is going to be the force from the spring, right? That's going to be in newtons. Now, in order for now I'm not going to be directly measuring the force. I'm going to be measuring the stretch when I put known masses on. So actually what I'm going to do is here's going to be the mass that I'm hanging. I'm going to, on the fly, convert it. Let's go ahead and do it in grams. That's fine. In grams, but I know that when I convert, I'm going to need to change it over to kilograms to turn that so that I make sure that I get out newtons for force. So let's see here. It looks like on the simulation, I can do masses from 50 grams up to 300 grams. So it might make sense to go up in nice even increments, maybe. Don't have to, but it'd be nice. And actually, we know that when we have 0 hanging on it, we know that the stretch is 0. And so we do know that value, so we can put it in as a data point. Can't always put 0, 0 in, but for this one, I know that when I have 0 mass hanging, the stretch is 0. And so that force of the spring is going to end up also being 0. We're going to put in 50 grams. Let's go up by 50s. That sounds good, because the biggest value they're going to let us use, it looks like, is 300 grams. That would be a factor of 6 times, and that fits our range. We want to have at least a factor of 5. So maybe just go up by 50s. So 100, 150, 200, 250, 300. Sounds good. Okay. Now my force, we're going to go ahead and make the spreadsheet calculate this force from the mass that we're hanging. And so to do that, I'm going to type equals, and then my equation. I want it to take what's in this box. I want to multiply it, I want to divide it by 1,000, because I want to go from grams to kilograms. And I want to multiply by 9.8. I'm going to do m times g, right? This mass in kilograms times 9.8 to get my gravitational force. Okay, now I'm going to take that formula and I'm going to drag this down, and then it will derive, go ahead and calculate out the forces we're applying already for us. And I can just put in my values here for the stretch that I measure in the experiment. I am all set up to go. Just for the heck of it, let's say that we're going to jump ahead here. I'll grab this. That one we can say we're going to insert a chart. Bam. Because I labeled the heads of my columns, it goes ahead and labels some stuff here for me nicely. But it doesn't recognize what kind of graph I want to do because I don't have the data points there yet. So it doesn't recognize it. I don't want a column chart. What I want is a scatter plot. Right? And because I don't have the data points in, it's just assuming that this is the first data point, second data point, third data point. So it's just making these values, 1, 2, 3, 4, 5 on this axis, which is not really what I want. Hopefully, once I put values in, it'll figure it out. We'll give it a shot. If it doesn't, I can always force it to do it the right way. So coming through, we have this. We said this looked like 8.5 centimeters. So in my chart here, I'm going to go ahead and put in 8.5 centimeters, 8.5. 2 decimal places will be 0.085. Right? Yeah. Okay. I can see what it's starting to do there. And then for this next one, we're going to go to 100 grams. So I'm just going to go ahead and move this to 100 grams. There we go. I can drop my movable line. Oh, I didn't like that. I don't like that. And there we go. Again, slide it down so it's at the tip of the arrow. That looks good. You say, what's that look like to you? Well, to me, that looks like 15, 16. I think it's right on the 17, 18.9 centimeters. What do you think? I will call it 18.9 centimeters. So I'll go to my chart. I'll put in 18.9 centimeters. That's 0.189 meters. Right. Go next value. I'm going to go to 150. Do, 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 do. Bink, 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 bink. There we go. 150. Take my movable line, put it down there to the end so I can measure very carefully the end, the length of that spring. If I was doing this in real life, I might be using some other straight edge against my ruler. What do you think? That looks like, does that look like 25, maybe 25.1, right? Let's see. So 0.251. Let's make this 200. Ding, 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 ding. There we go. My movable line. Forgot where is the end of the arrow there. I don't know. What does that look like to you? It looks like 31, 2, 3, 33 point. I'm going to call that 33.2. All right. Back to this. Let's make this 250. Oh, look at that. Spot on. Here we go. All right, we'll call that good enough. What does that look like? 41.3. Sure, sounds good. 41.3. And one last one. Setting this to the max value, 300 grams. Let that settle. That looks like 49 point. It's definitely past the halfway point. I'm going to call it 49.7. There we go. All right. This red line is not the one I want. These are my actual stretch values. This is what I want. Yeah, I'm not happy with the way it's doing that. I don't think I'm gonna let it bother me. Let's see. We just want this stretch versus force is what we want. This we want to be the stretch. There we go. See, that's what we're looking for. Okay, stretch versus force. And what do we want to do now? Well, now we want to go ahead and drop in our trend line. So we're going to go to series and we're going to say, hey, let's click the trend line. Bam, there it is. Look at that value. Look, I was really off on that one. That looks like that really looks like I totally misread that one. We'll think about that. My R squared. Label, use the equation. I got my equation here. I get an R squared value of 0.998, which I feel pretty dang good about. How do I feel about that data point being that way? Am I going to go back and retake that data point? Am I going to go ahead and strike out that one? How do you feel about that value? That looks like this was when I had a stretch of about, so the force was around 1.5. You say, that looks like that's this one. Do I want to check my stretch on that one? How picky are we going to be? You know, for our purposes here, what the heck? I'll go back and take a look at that value. Again, the 150 gram. Am I happy with how I read that? Bink, bink. You say, let's do our movable line here. What value does that look like to you? To me, that looks like, it really does look like 25 centimeters, 25 or 25.1 on the nose. What did I say it was? 25.1? Yeah, I don't know what to tell you. I don't know why that doesn't seem to fall right on the line like the rest. It's off by a teeny little bit. Am I going to let it bother me? No, nope, not going to let it bother me. Hey, there it is. There's my equation here. We're getting out. Now, this is the equation is not our nice formal mathematical model. 0.039, 5.98. So when I go ahead and take a look at that graph, and you say, hey, what are we doing here? We're getting a little y equals mx plus b from this. So if I go ahead and say, well, what am I getting here? I got this straight line graph that looks something like that. And it said, hey, if I do a little y equals mx plus b, here's my force of the spring in newtons, and here is my stretch in meters, right? Because we converted the units. You said we're getting an equation. My vertical variable is force of the spring. My horizontal variable is that stretch. My intercept, you said what the computer spat out for us here was 5.98x minus 0.039. Okay, that was the equation that that the program gave us. You say, so the x variable is actually our delta x, our stretch. You say 5.98. What would be the units on that? Let's do the intercept first. I'm sorry. Negative 0.039. You say, gosh, that number is really close to 0. Can we just say it's 0? And you say, well, I remember that the rule is that I can go ahead and I can say it's 0 if well, we use the 5% rule, right? You say two rules. One is it has to be within 5% of the median y value. You say, well, look, our median y value is around 1.5. 10% of 1.5 would be 0.15. 5% would be half of that. That'd be 0.075. And this is like less than 0.075 off from 0. So I think so that fits the 5%. You say we have to have a good reason. You say, do we have a reason to think this will go through 0, 0? And you say, sure. We know that when we had no mass hanging on the spring was not pulling, and so that force would be 0. Now, you could say that if we were taking legit data, that the weight of the spring itself would be making it extend a little bit, and that would give us a little bit of error built in, this kind of preloading from the weight of the spring itself pulling on itself, stretching itself. But we're not worrying about that here with this one. You say, gosh, this sure looks like that intercept ought to be 0, 0. And so we can go ahead and on our formula, go ahead and drop that intercept out, saying, yep, that's that intercept really should be 0. It's just a little bit of experimental error that we're, measurement error that we're getting that from. And so you say, so really I'm just going to have this. You say, now that slope, that 5.98, right? What would the units be on that slope? And you say, well, we'll give units measured by rise over run, so it'd be in newtons per meter. And so that is the formula that I'm getting, or rather, that's the mathematical model I'm getting from my experiment. And I can see from this model, I could plug in any amount of stretch and see how hard that spring would be pulling when the spring is stretched that far. And that's what we want. This relationship, you say in general, you say, think about the meaning, the secret meaning of the slope. And you say, well, when we think about what the significance is of a slope in a lab, we use this for every statement. And we would say, sure, we'd say, in this case, we'd be typing, see here, something like this. And you'd say, for every one blank of blank, the blank changes by blank, right? And you say that's what we write it for every statement. In this case, what we're doing is we're saying for every one, looking at our graph, what we're saying here is for every 1 meter of stretch, that was our variable on the horizontal axis. The force of the spring changes by 5.98 newtons, right? And so that's what it's telling us. You say, hey, it's telling us how much the spring, how much force the spring pulls with for every meter it gets stretched. So in this case, this is, if I just round it off really roughly for our discussion here, say that's 6, you say it says, hey, for every meter that I stretch it, it would pull with 6 newtons of force. What if I stretched it for a half a meter? Well, for a full meter, it's 6. For a half a meter, it's a nice linear direct relationship. So you say it's going to pull 3. If I stretch it a tenth of a meter, 10 centimeters, it had better be pulling with a tenth of 6, with about 0.6 newtons. Okay, so that's what this tells us. And you say, well, gosh, how much force the spring pulls with for every bit you stretch it? That's telling us how stiff or how strong the spring is. And you say, well, maybe that's worth giving a special name. And you say, sure. We say, well, we call this, you say, because this line, unlike the one I drew here, is a straight line, it's a nice straight line, we call this the spring constant, is what we call this, and we give it the symbol lowercase k. All right, so lowercase k, we call the spring constant. Because this is a straight line, it has a constant slope. Now, different springs have different stiffnesses. You can have really strong stiff springs and really weak flimsy springs. And so this K value will be different for different springs. But for a particular spring, that K should be the same value for small stretches and crushes. This equation is called Hooke's law. All right, that's spelled thusly. All right, that the force of a spring is equal to its spring constant times its stretch. I personally write Hooke's law a little bit differently. If we were to go and say we were to go ahead and do a, and you were to go ahead and take a look at like AP formula sheet because that, of course, is the equation that rules my life, the equations on the APC formula sheet. Then you can see here, if I kind of zoom in here, that they have the equation. Hooke's law shows up here. Where does Hooke's law show up on this sheet? Seriously, Dave? Oh, it's right there. Anyway, if I go ahead and look at this, you can see the way they're writing it. They have a little negative sign in front because what they want to do is they want to emphasize that the force of the spring pulls in a particular direction, and the stretch of the spring is in a particular direction. In other words, these are vectors. And you say that negative there is going to show you that whichever way you stretch the spring tries to pull back to get back to its rest position, its natural length where the force is 0. So when it's not stretched, when the stretch is 0, the force is 0. And you say, if I stretch it in the positive direction, the spring tries to pull back in the negative direction. That's why I've got that negative sign there to show direction. So the negative there in this way of writing Hooke's law is to show direction. The thing is, when we go to plug into F equals ma, right? When we actually go to solve problems with this equation, when we substitute in here, when we go to plug in this left side, don't we do like forces to the right minus forces left, or forces up minus forces down? In other words, we're putting a sign on it to show direction ourselves. So be careful. If you see a form of Hooke's law that looks like this, force of the spring is negative K times the stretch, right? Negative K times delta X or whatever. You say, be careful, because you don't want that negative is there for direction. And if you go and throw another sign on here for direction, right, you can see how you might trip yourself up there, counting for direction twice, And so you want to be careful about your signs with Hooke's law. So that's just a little problem-solving tip there for you when we plug Hooke's law into an F equals ma. All right. So Personally, I usually write it with a negative there to remind myself that the force of the spring is opposite the direction of delta x. I just have to be careful when I plug into sigmath to not do that negative twice. Okay, that's Hooke's law, derived from the Spring Lab. Should I show you the next bit? Sure, why not? I'll show you the next bit while we're at it. What I'd like to do now as a bonus is we'd like to go ahead and figure out the amount of energy that's stored up in a spring. So to do this, I'm going to take a look at my graph here. Now we did a graph of force versus the stretch of the spring, and you say, well, if I take a spring, or normally if I want to go ahead and think about energy, then we're using the equation for how much energy we've transformed from one type to another. We use an equation that looks like this. Not like that. We use an equation that looks like this, where we say the work done is the change in the energy of a system. And we know that we can, if I want to figure out a potential energy function, the way we do that is we take our system, right? And maybe there is some force acting on it, right? That's going to be pushing, right? Maybe that way. And we look at it as this object moves through some distance, right? And you say, hey, that I know that the work done by this force is equal to that force dotted with the distance it pushes through, right? And that's how we derive it. And so what we do usually is we say, well, gosh, maybe this is an electric force as this block gets repelled. Maybe this is charged up and it's getting repelled by some other charged object over here, maybe both positive or something. And you say, well, gosh, that's our electric force. And you say, if I want to find the potential energy for it, I just look a function that I could write for the electric force. I'll just look at the work done by the electric force pushing it, right? And I can say, well, that's like the amount of work that electric force does. You say, if I move this, this is a terrible example. I shouldn't be doing the electric example as my example because we're not quite so familiar with that yet. We're going to come back to that 2 units from now, actually. Let me use as my example. I got to use the gravitational one, even though I didn't want to. What we did with gravity was we said, hey, I have this object. And we said, what I'm going to do is I'm going to go ahead and I'm going to imagine lifting it up, right, against gravity. And as I do that, I know I'm storing up potential energy in the Earth object system. We said, well, to figure out how much energy I've stored up, really what I'm doing when I say it has a certain amount of gravitational potential energy is I'm saying because it's been moved up through this distance, gravity could now pull it down through that distance, and do a certain amount of work. So because it's here, gravity could do that much more work. So I can just measure that force, the gravitational force, and the distance it can pull through. And that's just going to be mg delta x. And you'll say, that's how much energy I just stored up. Well, that delta x, that's really the change in the height. And so we talked about the change in potential energy being mg times the change in height. That's the change in the gravitational potential energy I just gave the block. We'd like to do something similar with a spring. We'd like to say, and to make this easier on ourselves, I'm going to do this sideways, okay, instead of doing vertical. So I'm not going to be changing the gravitational potential energy. I want to do it so that here's this spring, and maybe that's the length the spring normally is. I have some block attached. We'll say that's x equals 0. Right, where the spring is neither stretched nor crushed. And we'll say, where the stretch is 0, if you like. And we'll say, all right, what I'd like to do is go ahead and stretch this spring a certain amount and know how much energy I've now stored up. Once I stretch this spring, that delta x, right, and now my spring is block is like over here now, right? And I've gone ahead and stretched that spring out. So now the spring is like work, 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 right? Okay, I know that spring, it is going to want to pull back, right? Pull that block back. And it can pull on that block through a distance here, right? Doing all this work, right? Speeding the block up. So there is energy stored up. It has the ability to do work, to pull through a distance. And so I'd like to calculate how much work it has, that it can do. The amount of work it can do, that's the amount of energy we've stored up in it, right? Because work's the transfer of energy, the amount of work I can do, the amount of energy I can transfer. And so you say, well, gosh, I just need to calculate how much work that spring would do because it's been stretched. And so you say, well, interesting. What if I had a different system, and maybe there is a nice constant force that's going to act on this while it moves through some distance, delta x. I could do a graph of that force versus the position. And if it's a nice constant force, I would get a nice graph like this. Maybe this is 5 newtons and it pulls through a distance of 10 meters. How much work would that force do? 5 newtons through 10 meters, work is force times distance. You say, gosh, that would do 5 times 10, that would do 50 joules of work, right? Or 50 newton meters or 50 joules. Wait, what's that 50 joules or that 50 newton meters of work? What is that on this graph? Well, 50, we got that by doing force times distance, 5 times 10. You say that's how we got that 50 newton meters. You say, but what's 50 on this? You say, oh, wait a minute, If I did 5 times 10, aren't I just calculating the area under the force position graph? You say, yeah, that's the work done by that force is the area on the force position graph. So when I go up to my spring, finally at last, and you say, hey, when I stretch this spring, the force of the spring, well, wait a minute. This is a triangle, right? Because the force is changing as it goes. The further I stretch it, the bigger the force of the spring gets. It's pulling more and more and more each bit. You say, so I just need to find the area of this triangle. And that would be the work, the energy I've got stored up in the spring, the work the spring could do. And so you say, well, gosh, calculating that area, you say, well, the area of a triangle, right, is going to be 1/2 the base times the height. And you say, and that's going to be, and we think that that area, that must have been A for area. Look at that, turn that triangle into an A. Area of that triangle. You say that's going to be the work done by the spring, or better yet, that's going to be the energy that we've stored up in the spring. We're going to think about it that way. Sorry. Is the energy stored up in the spring? Why did that not work? So I'm going to think about this as being that potential energy stored up in the spring as my U spring. Or better yet, we could call that U elastic, right? Okay, so it's going to be 1/2. Now, what's the base of a triangle? Well, the base of the triangle, that's just how far we've stretched it. That's just delta x. Now, what about the height? You say, what's this height here? Isn't that height value, isn't that the force of the spring, the maximum force of the spring, the force it had when it was stretched, that distance, delta x, that we're stretching it? You say, yeah, that's that max force, that force at delta x. How do I calculate that? You say, well, wait a minute, we just derived a formula for it down here, didn't we? We just derived that the force of the spring, we said right here, was negative k delta x. So I could put that in there, that k delta x. And so I'm going to have 1/2 delta x times k delta x. You say, gosh, that area, which is the energy we've stored up in the spring, is going to be 1/2 k times delta x, or 1/2 k times that delta x squared. And so that is going to be the formula for elastic potential energy stored up in a spring that obeys Hooke's law. And so that's it. And that's I believe, the last formula for this unit. So we've just derived two formulas here today. Hooke's law, the equation for how hard a spring is pulling as you stretch it, and the formula for the elastic potential energy, the energy stored up in a spring. All right, so that's two formulas out of this lab. What a deal. A few more comments I should probably make. As a side note, Hooke's law is named after Robert Hooke, who is this physicist, scientist who lived at the same time as Isaac Newton. In fact, there's this organization that was started in around 1661 in London called the Royal Society that still exists today. The Royal Society's mission is, of course, to advance science, and it's Britain's like big scientific institution. And when let's see here, so like here's the Royal Society's website, for example, and Robert Hooke was actually the first president of the Royal Society. He also is this guy. At first it was just this organization for scientists in London to kind of get together and talk science and talk about research. And his job was every week to come up with 3 or 4 little scientific demonstrations and explorations for them to consider. But Robert Hooke is maybe not quite as famous as he ought to be. You'd think the guy who started the Royal Society, which is the big organization for scientists in Britain, you'd think that he would be like really super famous. The problem he had was that he kind of ran afoul of Newton. When Isaac Newton went to present his first big paper to the Royal Society, it was about light. And Newton was thinking that light was made up of little particles. And Robert Hooke disagreed very strenuously with this, thinking that light was made up of waves. It was like a kind of wave that went through space. And so Hooke really gave Newton a hard time, and Newton like kind of withdrew the paper and then never published it again until after Hooke died. And so they kind of set them off. They were pretty cordial before that, but then after that, Newton really didn't like that. And eventually, after Hooke died, Newton became the new president of the Royal Society. And he really kind of set about tarnishing Hooke's reputation. And he had arguments about who first thought of this idea. The thing that Newton's, of course, really famous for is this idea that gravitational force is the same force that pulls things to the ground, is the same force that governs the motions of the planets and the moon up in the sky. And so Hooke kind of had talked to people. Hooke was this really bright guy who knew about lots of different things and had ideas, and he would give people these ideas, but then he would get on to something else. And Hooke wouldn't usually do the rigorous mathematical proofs of things. He'd come up with great ideas for testing things and equipment and give people ideas, but then he wouldn't do the full mathematical exploration that would be like the definitive proof of the idea. So he had talked to Newton and other people about this idea that gravity is this same force that moves things on Earth, moves things in space, and that it's this force that attracts planets to the sun and such, and that it's a force that gets stronger the closer they got. And that idea, influenced Newton, and Newton later on went and figured out and did the math and did the proof and showed that it was proportional 1 over the distance squared, the gravitational force, and so on. And then when Newton went to talk about this, then Hooke was outraged that he didn't get credit for the original idea and yada yada yada. But anyway, eventually after Hooke died, this picture here of Hooke, it turns out, wasn't painted until 2003. And that's because the only portrait of Hooke that we know of disappeared mysteriously once Newton became president of the Royal Society. There's these nasty stories that Newton had it burned, or that he purposely left it behind when the Royal Society changed buildings. Those haven't been substantiated, but that's the rumor. Getting back to this. So Hooke's law what I was going to say, again, Hooke was one who developed this. He first did the little math and experiments behind this, and so he gets credit. But something to know about Hooke's law is that when you take a spring and you stretch it, right, that force, the more I stretch it, the spring pulls back harder, harder, harder. But if you think about your own experience with springs, you know that when you go ahead and you stretch a spring, right, maybe my spring starts off looking, something like this, junk, 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 right? But as I stretch it and those coils get stretched out more and more, eventually that metal is going to be like really stretched. And at this point, if I want to stretch this thing anymore, it would be like I'm actually like, really distending the metal itself instead of just the coils. You know what I mean? And so this force graph, right, instead of being this nice linear graph, at a certain point, isn't it true that force of the spring would kind of suddenly get bigger, 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 like, you know what I mean? As you start not just undoing the coil, but you're actually now like stretching the spring. Wouldn't this kind of zoom up like that? Same thing if I take that coil and instead of taking from right here, this is where I like to call it the stretch is 0. I like to call this X position 0. You say instead I'm going to start scrunching the spring. I'm going to start crushing it down. And when I do that, those coils are going to get closer together now, right? Okay, as I scrunch it more and more, eventually those coils are like slammed up against each other, right? And so this graph actually, if I go back to that, you say, it's going to be this really nice linear that goes through 0, 0, right? And you say, but eventually, so now I'm pushing in the negative direction, right? Over here, my X's are negative, right? And over here, my X positions are positive. You see over here now, as I scrunch it down, I crush it to the left and the force of the spring would get bigger and bigger. But you say, but eventually it would zoom down, right? Once those coils get like pressed into each other, right? Now I'd have to actually smush the metal. And so the point is, Hooke's law is really only applies over a certain range, right? It only applies when you're dealing with forces, with stretches that are relatively small. Hooke's law only applies to small stretches and crushes, right? Right? Because if I crush it down too far, I'm going to have to start smushing the metal to get the coils to crush closer. And as I stretch it out, I'm going to have to start actually stretching the metal itself into a thinner wire. And so Hooke's law just recognized that it has a limited regime over which it works. And the other thing is, so Hooke's law is not like a great big huge law of nature. It has restrictions. And the other restriction is, turns out not everything that's stretchy will give you a nice linear graph at all. There are some materials that when you stretch them, right, your graph will not be a straight line. You might get a graph when you stretch it that maybe it starts curving right away, right? You know what I mean? And so something that looks more like maybe is that like a tangent graph? Anyway, but you get the idea. In my mind, I was thinking about having an equation where maybe the force of the spring, it's not a linear, maybe it's proportional to, X squared or X cubed, right? Okay, there's some materials that that force changes much more rapidly like that with stretch, not in the linear way. So just saying, Hooke's law is not a general law of nature. It's more like Hooke's useful guideline in that it does work for a lot of cases, but not all the time. For our purposes in honors physics, we will always work with what are called ideal springs or Hooke's law springs that do in fact obey force is negative kx, k times the stretch, and that the energy stored up would be 1/2 k times that stretch squared. In AP Physics next year, we'll take a look at cases that are a little bit trickier, where we can have objects then that don't obey Hooke's law, and we can still figure out how much energy is stored up by figuring out the area under that weird, wacky curved graph. And to do that, we'll use a little bit of calculus, but that's for next year. So that's essentially kind of what I have to say here about Hooke's law and the energy stored up in a spring. I guess I've got one more special tip to give you, though. All right. And that's a tip about when you're doing problems where the spring is set up vertically. If I'm doing a problem where I've got a vertical spring, okay, and I'm going to go ahead and hang a mass on it, and then that's going to stretch the spring out, some distance, right? If I'm doing energy calculations, I might very well be looking at a case where as this thing is wiggling back and forth when I let go and I drop it or whatever, where I'll be changing the kinetic energies, it changes speeds as it wiggles back and forth, right? Right? It'll wiggle back and forth, getting faster, getting slower, and so on. You say, but not only will I be doing that, you say, well, besides that, I'll be changing the energy stored up in the spring. There'll be a delta U elastic. And not only that, I'll be changing the height of the spring, so I could have a delta U gravitational. If I include the Earth in the system, I include the spring in the system. And so what's going to make my life easier, when I plug into this delta UE, I'll be looking at my final minus initial. So I'll be looking at the final elastic minus initial elastic. That'll be a 1/2 K times that final stretch squared minus a 1/2 K times my original stretch squared. Right, to figure out the change in that energy. Right, and when I do the gravitational, that would be a 1/2. What am I doing? A 1/2? That's crazy. That's going to be formula for gravitational energy is mgh. That would be my mg times the final height minus mg times my initial height. But here's the deal, right? When I go to do this, right? Okay, and then of course I'm going to have my changes in my 1/2 mv final squared minus 1/2 mv initial squared. Okay, good enough. Anyway, that'll be that, right? And then it might be an outside force, someone grabbing it, yanking or something, doing work or whatever. But anyway, point is, it will make my life easier. If as this guy's wiggling back and forth and I'm changing my X value, when I do that, my position of the spring, I don't have a choice. X equals 0. The stretch of the spring has to be 0 at that point where the spring wouldn't be stretched or crushed. Okay. This is not the position the block would hang at. This is just the position where the force of the spring is 0. That's got to be my X equals 0 equation, because that's where the force of the spring would be 0. Right? Because force of the spring is negative kx. And you say, so when this x is 0, that's when the force is 0. Okay, so that has to be, those have to go together, right? And so that's where there's 0 energy stored in the spring too, is when the spring is not stretched or crushed at all. So the point is, I'm also going to need a variable for height, aren't I? So as the thing goes up and down, I'm looking at the stretch position, right? Calling this x equals 0. But I'm also going to need to have a variable for height as it goes up and down and be talking about the height. So you say, well, gosh, if I'm changing the height up and down, changing x position of the spring up and down, wouldn't it make my life easier if this h and the x, if I called the same spot 0 for both? So if I say, hey, at this spot, we'll also say that's also where height is 0 for the block. And that way, h and x, instead of being 2 different variables to have to solve for, that would just become 1 variable to deal with instead. And that will make it easier to solve when I have an unknown height. So that is the trick, is to say x equals 0 and h equals 0 at the same height. It will make your life easier. The other thing that's important then is when we deal with heights, upward has to be the positive direction, right? Otherwise, if I made downward the positive direction for height, it would screw up my energy changes. I'd have something going up and it would be losing potential energy instead of gaining it. So that means I also have to call up the positive direction for x when I deal with a vertical spring, if I'm going to set those variables equal to each other. And say h equals x. Okay, there. That's pretty good. That's what I have to say about Hooke's law and elastic potential energy, and a little tip for working with vertical springs. All right, and that, I'm going to end the video at that point.